Hello everybody, this is another look at Rust programming language references and borrowing. So the big difference between Rust and C, C++, or even Python for that matter, is this concept of borrowing. Now, I'm on the documentation for Rust, and I've also looked at some other documentation, which, funnily enough, it's actually Microsoft, learn.microsoft.com. And they've got some take your first steps of Rust, understand how Rust manages memory. If you can find that, I'll put the link in the description. So what we're covering with borrowing is the difference between working on a copy of a variable, also called a binding in Rust. So slightly different terms. So binding, variable, we'll stick with variable. Anyway, back to the Rust, the excellent Rust documentation, and we are looking at an example. One of the great things about the Rust documentation is the ability to run the examples within the documentation, which I think is excellent. So let's start. The issue with the tuple, I still don't know how to say that, tuple code in listing 4.5 is that we have to return the string. So basically the previous example was a traditional example where we had a function returning a string. But what we were doing was we were taking the string, working on it, and then passing it back. I mean, that's typically what you would do in Python. However, this is the crux of borrowing in Rust, and what we're doing, if you're familiar with C, then you've probably seen this all before, but I'm just going to cover it. Here you would define a function called calculateLength, and it has a reference to an object. So the reference, borrow, reference, again, they're kind of interchangeable. So a reference is like a pointer in that it's an address we can follow to access the data stored at that address. Unlike a pointer, a reference is guaranteed to point to a valid value of a particular type for the life of that reference. Lifes we'll get onto in due course, but for now we just need to know that ampersands represent references, and they allow you to refer to some value without taking ownership of it. The whole concept of ownership is something unique to Rust, or as far as I know, amongst the main languages. So function, calculateLength, and we pass in the reference. So rather than taking a copy of the variable, it's actually, which would have been S, so it would have made a copy. It's just, in this instance, it would have made a copy of S1 if we were doing it let's call it the old-fashioned way. All it's doing here is it's finding the reference, and we'll look at the theory in a minute, but let's just run that. So there's no s.len is being returned by the function, but we're actually printing two things. So we're printing an updated version of S1, and S1 equals, to start with, S1 equals the word hello. Let's run it. The length of hello is 5. So the length of, and in there we're putting S1 into the first pair of curly braces, and we're putting len into the second pair of curly braces. So as you can see here, this function worked, or actually it read what was stored here. So what I've got highlighted here in blue is effectively this here when it gets called. So, and S1, which is the word hello. So calculateLength is passing back the length, and that's why it's usize. So usize is because it can, rather than just passing back a U32 or an I32 is passing back the usize because it does vary from compiler to compiler. We won't worry about that for now. Let's look at the theory. So first notice that all the tuple code in the variable declaration and the function return value was gone. So that's the previous example where we were calling a function, doing something, and then passing the value back. Second, note that we pass ampersand S1 into calculate length, and in its definition we take the ampersand string rather than the string. These ampersands represent references, and they allow you to refer to some value without taking ownership of it. So because we are dealing with a string lives on the heap, the memory heap. So we have here the S, which is basically a pointer, which is pointing to S1, which is a pointer, which is pointing to the heap. So rather than let me just scroll down and I'll try and find the other example. It might be in the previous page. I just want to show you the alternative way. There we go. So that's just having a pointer pointing to the heap. That's having one pointer pointing to it. That's having a second pointer pointing to the same string, which is fine. This is what you would actually have if you had two variables pointing to a string hello in Python, for instance. You'd have S1 and S2, and you've got a copy. I'm not going to go into deep copy, shallow copy, and everything here, but if you're interested, look up deep copy, shallow copy. Rust automatically calls the drop function and cleans up the heap memory for a variable. So when a variable goes out of scope, Rust cleans it up. That's the whole point of borrow, and they go on to talk about dangling pointer, and you see they talk about shallow copy and deep copy with other languages. So yeah, come to this documentation, but for now I'm just going to run these examples. So we've seen how in the first example up here, when you run it, all that's getting returned is the length. And we've got a playground connection timeout. Oh well, moving swiftly on. Right. Yeah, quick note. The opposite of referencing by using the ampersand is dereferencing, which is accomplished with the dereference operator, which is the asterisk. So if you're familiar with C, that'll be the asterisk and the ampersand kind of can work together. We'll see some uses of the dereference operator in chapter 8 and discuss details of dereferencing in chapter 15. I'm not going to cover that here. Let's look at a closer look at the above function call here. So the ampersand S1 syntax lets us create a reference that refers to the value of S1 but does not own it. Because it does not own it, the value it points to will not be dropped when the reference stops being used. Likewise, the signature of a function uses ampersand to indicate that the type of the parameter S is a reference. Let's add some explanatory annotations. So here we go. Calculate the length. Pass in a variable called S, which is a reference to a string. As says there. Here, S goes out of scope, but because it does not have ownership of what it refers to, it is not dropped. The scope in which variable S is valid is the same as any function parameter's scope, but the value pointed to by the reference is not dropped when S stops being used because S doesn't have ownership. So basically that value is still living on the heap and it's still accessible by the main function. When functions have references as parameters, instead of the actual values, we won't need to return the values in order to give back ownership because we never had ownership. I know this is quite, to start with, the first time you ever read this, you'll just think, oh my, I'm never going to understand this. If it helps, maybe Actually, if you go and look at C and look at address of operators and pointers, and then you come and look at Rust, you might actually think Rust is easier in some ways. But if you come in from Python, this will probably be a bit of a culture shock, but just hang in there. So we call the action of creating a reference borrowing. So that's the Rust phraseology. As in real life, if a person owns something, you can borrow it from them. When you have done, you have to give it back. You don't own it. So what happens if we try to modify something we're borrowing? Try the code in listing 4.6. Spoiler alert, it doesn't work. So let's think why it doesn't work. They've already kind of given us a hint here. We're trying to modify something that we're borrowing. So down here, we're borrowing. We borrow some string, and then we try and push world onto the end of it. But we're borrowing it. We're borrowing. So when we call it, we're borrowing S. So S originally comes from here. But if you remember, it's immutable. So if we come down here, when we compile it, we will get, consider changing this to be a mutable reference. Just as variable names are immutable by default, so are references. We're not allowed to modify something we have a reference to by default. We can fix the code, allowing us to modify a borrowed value with just a few small tweaks that use instead a mutable reference. So mut or mute. I would say mut, but it's actually said mute, as in the first part of the word mutable. So we add mute there to just say that the word hello basically is mutable. Then with our function prototype, we also say that we're going to be passing in a mutable string. So from there, that's kind of matching that bit. So we're passing in a mutable string, and then that mutable string called some string, we will then push comma world onto the end of it. And to keep it all the same, matching, because we're passing in ampersand mut there, we have to pass in ampersand mut when we actually call it for real. So we're passing in ampersand mut s, which is effectively, or what we're saying is mut s, and we use the ampersand here because we want to borrow it. So that, and also if you wanted to, you could leave a space between the ampersand and the mut. I know there's a lot of debate in C about, there's no output, it just runs, there's no error though. There's a lot of debate in C about whether you should leave the space between the asterisk and the variable name or not, but first we change S to be mute, then we create a mute. This is referring to what we've just done here. So first we change S to be mute, then we create a mutable reference with ampersand mute space S where we call the change function and update the function signature to accept a mutable reference with some string colon ampersand mute string. This makes it very clear that the change function will mutate the value it borrows, and it's borrowing the value from here, which is our first variable inside main. Mutable references have one big restriction. If you have a mutable reference to a value, you can have no other references to that value. This code that attempts to create two mutable references to S will fail. So you have your original value here. You create a new variable that's basically saying make reference that original. Now you've got a second one. Cannot borrow s as mutable more than once at a time. And the reason why that is because of the data race, or the potential for a data race. So here we go. This error says that the code is invalid because we cannot borrow s as mutable more than once at a time. The first mutable borrow is that one there. The first mutable borrow is R1 and must last until it's used in the print ln. But between that creation of that mutable reference and its usage, so in between here and here, we tried to create another mutable reference in R2 that borrows the same data as R1. So R1 and R2 are both borrowing from mutable S. The restriction preventing multiple mutable references to the same data at the same time allows for mutation, but in a very controlled fashion. It's something that new Rustaceans struggle with because most languages let you mutate whenever you'd like. The benefit of having this restriction is that Rust can prevent data races at compile time. A data race is similar to a race condition and happens when these three behaviors occur. Two or more pointers access the data at the same time. At least one of the pointers is being used to write to the data. There's no mechanism being used to synchronize access to the data. So basically you've got a chance of two different pointers modifying the same piece of data. Data races cause undefined behavior and can be difficult to diagnose and fix when you're trying to track them down at runtime. It's a bit like being in, being at a party and you've got two people talking to you. In the end, you can't tell what you're trying to concentrate on, what one's saying to you, what the other one's saying to you, and in the end, you're not actually understanding what either of them are saying to you. Rust prevents this problem by refusing to compile code with data races. As always, we can use curly brackets to create a new scope, allowing for multiple mutable references, just not simultaneous ones. So you can have multiple ones, but not at the same time. So these curly braces here create a new scope. R1 goes out of scope here at the end of this scope, so that's always the end of the scope when that curly brace closes. So we can make a new reference with no problems. So we've got R1 equals ampersand mut of S, close the curly brace, and then let R2 equal ampersand mut of S. And I think if we run that, we should just get no errors. Yeah, no output. Rust enforces a similar rule for combining mutable and immutable references. This code results in an error. So the reason we've got the error here is because we have got ampersand S for R1 and R2, and then R3 is ampersand mut S. So R1 and R2 are kind of borrowing S in good faith. And then R3 could just come in and completely modify the value of S. And then R1 and R2, when they're called here, could end up completely displaying something which they never intended. We cannot also have a mutable reference while we have an immutable one to the same value. Users of an immutable reference don't expect the value to suddenly change out from under them. So yeah, R1 and R2 don't expect the value to change, which it could change because R3 could potentially modify it. Big problem. Users of an immutable reference don't expect the value to suddenly change from out from under them. However, multiple immutable references are allowed. Multiple immutable references are allowed because no one who is just reading the data, so you can borrow the data, but just not make it mutable, has the ability to affect anyone else's reading of the data. Note that a reference's scope starts from when it is introduced and continues through the last line that reference is used. For instance, this code will compile because the last usage of the immutable references, the println exclamation mark here, occurs before the mutable reference is introduced. So R1 and R2 are basically read-only. That's fine. And then println, that's all done and finished with. Then R3 is created, and R3 is a mutable borrow of S. And that's fine, that will run because R1 and R2 no longer present. So println here, as I've got highlighted, will result in hello and hello. Then these two variables on the stack are finished with, so they're no longer needed, they get cleaned up. And then we create R3, and that just says that ampersand mute S, hello, R3, then we print it. So that's where we get the hello from, that line there. This is quite detailed and it's a lot to take in, but maybe read it twice or watch this video twice. The scopes of the immutable references R1 and R2 end after the println, where they are last used, which is before the mutable reference R3 is created. These scopes don't overlap, so that's the important thing. So this code is allowed. The ability of the compiler to tell that a reference is no longer being used at a point before the end of the scope is called non-lexical lifetimes, or NLL for short. And you can read more about it in the edition guide. So we're nearly done. Even though borrowing errors may be frustrating at times, remember that it's the Rust compiler pointing out a potential bug early at compile time rather than at runtime, and showing you exactly where the problem is. Then you don't have to track down why your data isn't what you thought it was. So yeah, it's like guardrails really for you. Dangling references. Dangling references is basically when you're trying to specify something from an address or a reference which hasn't ever actually had anything assigned to it. So let's just read through this and then we'll be done. Dangling references. In languages with pointers, it's easy to erroneously create a dangling pointer. A pointer that references a location in memory that may have been given to someone else. By freeing some memory while preserving a pointer to that memory. In Rust, by contrast, the compiler guarantees that references will never be dangling references. If you have a reference to some data, the compiler will ensure that the data will not go out of scope before the reference to the data does. So we're going to see an example just here where there's the reference, but there isn't actually any data. So let's try to create a dangling reference to see how Rust prevents them with a compile time error. So we've got a reference to nothing, which is just a variable, and then we've got dangle, which is the function, and then we are saying Dangle returns a reference to a string, and then hello, so s equals hello, and then we're going to pass back ampersand s, but we get the error. Compiling FN dangle string expected named lifetime parameter, blah blah blah. This error message refers to a feature we haven't covered yet as lifetimes. We'll discuss lifetimes in chapter 10, but if you disregard the parts about lifetimes, the message does contain the key to why this code is a problem. This function's return type contains a borrowed value, but there is no value for it to be borrowed from. So when we call this function dangle, there is no value. S is only lives within this function. Because S is created inside dangle, when the code of dangle is finished, S will be deallocated. But when we tried to return a reference to it, that means that the reference would be pointing to an invalid string. That's no good. Rust won't let us do this. So rather than send back a reference, we actually just pass back return S itself. So rules of references. Let's recap what we've discussed about references. At any given time, you can have either one mutable reference or any number of immutable references. So if you're going to change it, you can only change it in one place. If you're going to do read only, you can do it as many places as you want. And then references must always be valid. So you can't send back, you can't have a reference to something which doesn't exist. That is, I know that's been a lot to take in. It is for me as well. But I think nail this, and I meant to press F11. It's getting dark. Sorry about that. Wrong button. Wrong button. There we go. Yeah, and I'll put the links to what we've just read, and don't forget that you can read this documentation, and many places you can run the code as well within the article, which is really nice. Also, the page before, I'll put in the link to that as well, so the stack and the heap. Many programming languages don't require you to think about the stack and the heap very often, so yeah, e.g. Python. But in a systems programming language like Rust, whether a value is on the stack or the heap affects how the language behaves and why you have to make certain decisions. Parts of ownership will be described in relation to the stack and the heap later in this chapter. So here it is, a brief explanation. And then there we go. That's all there for you to read. So yeah, thanks for watching this video. And I hope you at least learned something or had some inspiration, and you can go off and now at least come and look at documentation and try and get your head around borrowing, references, dangling pointers, ownership, and you can also come and look at take your first steps of Rust, understand how Rust manages memory on the learn.microsoft.com site as well. So yeah, thanks for watching, and I'll be back with more soon.